and also that have dialed in. I have quite a set of people here in the room, quite a number. Just going around the room, John Lund is here. He's the subsurface mooring lead. Chris Newhall is the refurbishment lead. Matt Palanza, the electrical lead. Stephanie Patillo is the software lead. Eric Benway is the operations lead. Sherry White is the systems engineering, lead systems engineer. Al Pudeman is here. He is one of the Coastal Global Scale Nodes project scientists. Peter Brickley is the glider and AUV operations and shoreside operations lead. Kim Sargent is the business operations lead. And finally, Rebecca Travis is one of the lead instrument technicians. Sherry White will be providing the presentation. I believe the slide count is about 74, 60 roughly, 60 to 74, and I think the questions and answers will follow after her presentation. Alternatively, you can issue questions online through the interface. Leslie, anything more to say before Sherry gets started?
Nope, I think we're good.
And are we getting this recorded?
Yes, we're rolling.
Okay. And I'll also mention we have Ed Dever at Oregon State University, and
John Fram is the lead systems engineer out there.
So we went through the introductions, but in case you didn't catch everybody's name, here's the list of key people that are responsible for the OOI segments at OOI, which we call CGSN, and at Oregon State, or EA, Endurance Array. Most of these people are on the line, except for a couple of our project scientists and John Fram. So the plan for this webinar is we're going to go through the full overview of the infrastructure that is being deployed as a part of the Coastal and Global Scale Nodes, including the uncabled portions of the Endurance Array. So we'll start with the overview of the arrays. There's some details on the science instrumentation, mooring details for each type of mooring. We'll go into the different types of vehicles that are being deployed, and then the opportunities related to these arrays, how you can add instruments to the infrastructure, or alter the sampling strategies, or participate in cruises, and what the proposal and integration process is. And as Leslie said, we'll have time for questions at the end. So just to start off, there are a number of OOI science themes that are addressed by all of the different parts of the OOI array. These are the themes that are addressed by the Coastal Pioneer, Coastal Endurance, and Global arrays. You'll see there's missing a few numbers there. Those are the science themes that are addressed by the seafloor cabled array off the West Coast. This is all stuff that is from the OOI science prospectus from back in 2007, so you can look up that document for more details on that. We're going to start with talking about the global arrays, and you can see there are 4 global arrays located in the high latitudes, North and South, Pacific and Atlantic Oceans. The arrays are nominally all the same. There are some minor differences that I'll mention. And there's some kind of specific terminology to these arrays that if you get the terminology down, that'll make understanding some of the future slides a little bit easier. The global moorings are laid out in a triangular array. One corner is called the apex, and that has a surface mooring and a subsurface profiler mooring. The other 2 corners of the triangle consist of identical flanking moorings that have fixed instrumentation. Those flanking moorings are also subsurface moorings. The one difference in that is the Station Papa array in the North Pacific does not have a surface mooring. There is a NOAA surface mooring in the vicinity of that array, which kind of serves the purpose of the surface mooring. Additionally, there are nominally 5 gliders that are deployed at these arrays. 2 are called profiling gliders, and they operate in the vicinity of the profile and mooring, so they're making profiling measurements in the upper 200 meters. The other 3 are open ocean gliders, which swim around the periphery of the array, collecting data in between the moorings, and they also communicate acoustically with the subsurface moorings. And we'll talk about that a little bit better. So when you think about the orientation, apex is the point where the surface mooring and the profile mooring is. The one extra thing I will note is at the southern arrays, Southern Ocean and Argentine Basin, they have only 1 profiling glider. So starting with the Station Papa array, this is located in the Gulf of Alaska, nominally 4,250 meters water depth. That apex of the array, as I mentioned, that's the part with the profile mooring, is oriented to the west-southwest. As I said, there's no surface mooring in this area. This is an area of strong winds and waves with moderate to low eddy activity. It's an area where there's a long history of observation, which is one of the reasons we're there. Details about all of these arrays are captured in site characterization white papers that have been written and published. You'll see the document numbers printed on the slide, and that documentation is all available through the OOI website if you want to dig in to a lot more detail.
Sherry, I don't know if it's worth it to break in at this point. I'm going to be the chief scientist on the global Papa array cruise this summer. OOI folks are going to provide the deck leads. OSU folks are going to prepare instruments. But I guess to the point of people that are interested in the Station Papa array, I am going to attend the 9 to 10 March meeting at iOS in Sydney, British Columbia this spring or this late winter to talk about upcoming Papa field activities.
Thank you, Ed. Moving on to the Erminger Sea Array. This is in the North Atlantic, just off the tip of Greenland. This is our shallowest of our global arrays at 2,800 meters water depth. In this case, the apex of the array is pointed to the north-northeast, such that our flanking moorings, those are the 2 subsurface moorings, are in line with the OSNAP moorings. That's the program looking at overturning in the subpolar North Atlantic program, something similar to that. So our flanking moorings in that array also have extra instrumentation at depth that matches instrumentation on the OSNAP moorings. So we're working in collaboration with that project. This is an area with really strong winds and waves associated with the tip jet, which you can see in the image there on the right. A lot of high eddy activity here. Once again, you can see the document number for the site characterization paper. And as Ed mentioned, he'll be chief scientist on the Papa array. The other global arrays will be run out of Woods Hole Oceanographic Institution. The Southern Ocean Array is the array at 55 south, 90 west off the coast of Chile. This is about 4,800 meters water depth, and the apex is pointed to the south. It's another area of strong wind and waves and atmospheric forcing, area where Antarctic intermediate water is formed. These cruises will go in and out of Punta Arenas, Chile. And then the last array is the Global Argentine Basin Array. This is our deepest global array at 5,200 meters. The apex is oriented to the south. Strong wind and waves and atmospheric forcing, a lot of eddy activity, and an area where you actually get bathymetric mud waves, so there seems to be a lot of activity throughout the water column all the way down to the seafloor. So those are the global arrays. We have 2 coastal arrays, the Endurance Array on the west coast, which is operated by Oregon State University, and the Pioneer Array here on the east coast, operated by us at Woods Hole Oceanographic. The Coastal Pioneer Array is located just due south of us, basically on the shelf break front. You can see in the diagram to the right the Gulf Stream going up to the right, upper right, and then the coastal current coming down along the other side, and lots of mixing happening in the vicinity there of the shelf break, making this a very interesting area. The array is laid out like this. There are basically 10 moorings in the array. There are 3 surface mooring, profile mooring pairs. If you can see my mouse on the screen, there's a pair of moorings at the inshore site, a pair of moorings at the offshore site, and a pair of moorings at the central site. There are then 4 single coastal profile moorings that are at the other corners and in between on the main line. So we have the main line and the upstream line. There are also 6 gliders that operate in the vicinity of this array and 2 AUVs. And the details of those we're going to get into later in the presentation when we focus on the vehicles. The endurance array consists of 2 lines of moorings, the Washington line and the Oregon line. There also consists of profile mooring, surface mooring pairs as the Pioneer array, and there are also 6 gliders that operate in the vicinity, kind of along the red lines you see here. As I said, we'll talk about the gliders in more detail later. Here's an overview of what the mooring lines look like. This is the Washington line, where you've got a surface mooring, profile mooring pair at each of the sites, offshore, shelf, and inshore. These are the same moorings that are deployed here on the Pioneer array. So when we talk about them, the infrastructure is the same in both places. The Oregon line, we have the same pairing of moorings as on the Washington line, the difference being the cable from the cabled array operated by the University of Washington comes up into this region. And so there is no instrumentation on the seafloor on the moorings at the shelf and offshore sites because that instrumentation is located on these subsea packages that are cabled. The cabled array group did hold an informational meeting previously. If you're interested in what's going on the cabled array, either in the endurance region or out at the other axial and hydrate sites, you should get in touch with the University of Washington group.
And I'm happy to pass on questions as well. If you want to bring them here, I'll take them down and relay them as well.
Yeah, and the webinars that have been held previously are typically posted to the OOI website. So if you miss one of the webinars, you can get it from the website, and I think some of them are posted to YouTube. Okay, so we'll do a quick overview of the instruments. These are the core instruments that are part of the OOI infrastructure. So there's a number of instruments that we deploy throughout the arrays. It's a little bit of an eye chart, but we have the name of the instrument type here. We use a 5-letter code for all of our instrumentation. So throughout this presentation, and if you're digging around on the OOI website, looking at documentation or looking for data, these are the codes that get you to those instruments. So this is a little bit of a cheat sheet. Maps the 5-letter codes to what you might be more used to, either in terms of instrumentation names or vendor and model names. So we measure a variety of things, conductivity, temperature and depth, pressure, oxygen, velocity in various forms, waves, bulk, meteorology, and direct covariance flux. We have fluorometers, optical attenuation and absorption instruments. We measure PAR, spectral irradiance, nitrate, PCO2 in both air and water, pH, and we have bioacoustic sonars for detecting zooplankton, and we have cameras on the West Coast site. So there is a lot of instrumentation throughout the sites. As far as the interfaces, how these instruments or any future instruments may interface with the CGSN and the uncabled portions of the array, they can either be self-powered instruments running on alkaline or lithium batteries, or they can be powered by our infrastructure. The portion of the infrastructure, the platform control that the instruments plug into, we call the DCL, which is Data Concentrator Logger. It's an electronics package that provides power and data logging capabilities so that we can communicate with the instrument, log the data, and give new commands as needed. The power we provide through our moorings is either 12 or 24 volts. In terms of communications, instruments, of course, can be self-recording, and even if they are self-recording, most communicate with the infrastructure either through inductive communications or serial or Ethernet direct connections. And then they are mounted either with custom clamps to our infrastructure, such as the tower, the buoy, the frame, or through clamping directly to the inductive wire, such as the CTDs, microcats, and such. And how the instruments are actually operated for sampling is captured in this OOI document. You see the document number here, 1102-00200. This is the OOI observation and sampling approach, and it outlines what the baseline is, so how every instrument should be operated over the course of the program to get, a good data set for long-term measurements, and then how we actually are operating in some cases where we, due to availability of power communications, we're actually operating faster than we need to. Okay, so now we'll go into the mooring details of each of the types of moorings. We have basically 5 different types of moorings that we deploy, but they can kind of be grouped into 2 classes. Those that have a surface expression, the coastal profiler moorings, the coastal surface moorings, and the global surface moorings. They actually have a common platform and data logging systems, a common satellite and line-of-sight communication systems. The surface moorings have their own power generation, whereas the profiler moorings operate on batteries. The subsurface moorings are the global profiler mooring and the global flanking moorings, which are deployed for a year, so they're long deployment, no potential for power generation, so they are battery powered. They have special low power platform control and data logging systems, and they communicate through acoustic communications with gliders, which serve as data mules. So we'll go through each type of these. The coastal profiler moorings are moorings that have these wire-following profilers that crawl up and down the mooring line. In this case, we're using the McLean MMP, McLean Moored Profiler systems. There are 7 of these at Pioneer. You can see all of the 7 sites we have at the Pioneer Array have these coastal profiler moorings. The inshore and the central sites actually will only deploy them in the wintertime. In the summertime, will be gliders that operate in that vicinity instead. And we have 1 mooring of the same design that is on the Endurance Array at the Washington offshore site. This provides the details of the coastal profiler mooring and a small sketch of what it looks like. These have a submersible surface buoy, so it can actually get sucked under if wave conditions get too extreme. It has a basic telemetry on the tower. The power is all provided by primary batteries in the buoy. There's then a stretch hose component, which couples the telemetry and platform control to the rest of the mooring, but the stretch hose enables us to decouple the motion of the waves from the lower part of the mooring. A sphere, 64-inch sphere, provides the buoyancy to keep the lower portion of the mooring taut so that the profiler can go up and down the mooring. And then at the bottom, in many of the cases, we have an ADCP that's housed in a frame, and then below that is the recovery buoyancy and the anchor with line pack. We do have to recover everything we deploy, including anchors, so we have recovery line packs on all of our coastal infrastructure. This shows some of the components of the profiler moorings. So you can see the plane profilers. These are the buoys and the anchors, the subsurface sphere, and the ADCPs, and the line packs for the anchors. So the way these moorings work, these are the lower power of the coastal moorings. They use a simple controller that is primarily asleep to save power. The profiler itself operates on its own schedule. It does its profiler. It then calls to wake up the STC, which is the sensor and telemetry controller. It downloads the data through inductive communications to the STC, and then once that's done, the STC calls out to any other instruments, the motion pack, the inductive ADCP, gets any data it can from them, and it then It then can telemetry that data back to shore. If there's any updated information from shore, that then gets sent back to the mooring, and then it goes to sleep and waits for the next cycle. In terms of potentially adding instrumentation to these moorings, there's a few possibilities. Instruments can be strapped onto the submersible surface buoy or onto the 64-inch sphere. There's a little bit of room on the inductive line above and below the profiler stops. Obviously, you can't do anything in the middle because that's where the profiler goes up and down. And there's some room in the ADCP frame. The addition of any instruments to these locations will require some reanalysis of the mooring due to the added weight and drag to make sure it still operates as designed and safely. Additionally, there could be instrumentation added to the profiler itself. That would require a design change of the profiler by McLean, the vendor of the profiler. Surface moorings. So you'll see here the locations of the surface moorings at Pioneer and at Endurance. We use a lot of different terminology because there are some slight differences between some of these surface moorings. So bear with me, I'll try to be clear on what is what. Here at Pioneer, we have 3 surface moorings. These are all considered high-power surface moorings that have instrumentation at the surface, in the water column, and on the seafloor. There are 2 of these high-power surface moorings on the Washington line of the Endurance Array at the shelf and offshore sites here. There are similar moorings at the shelf and offshore sites of the Washington Array. These are what we call more standard power moorings because they do not send power to the seafloor. This is a location where I mentioned previously the cabled array comes up to these sites, and so any seafloor instrumentation is actually connected to the cabled array rather than to our moorings. And then there's 2 more surface moorings at the inshore sites of both the Washington and the Oregon line. We'll refer to these as the EA inshore moorings, and these are a little bit special due to the very shallow water depth, 25 meters water depth. So they have to use the smaller submersible surface buoy like we use on the profiler moorings, but then the infrastructure below the surface is all the same as the other surface moorings. I'll try to show you the difference between those in this graphic here. So the inshore moorings, as I mentioned, have the smaller submersible buoy, whereas the rest of the moorings use this larger coastal surface. So the telemetry is all the same. The platform control components are the same. The submersible surface buoy version uses batteries, so there are batteries both in the submersible surface buoy and in the multifunction node on the seafloor, which is this portion down here. The standard coastal surface buoy contains rechargeable power systems, so wind turbines, solar panels, and rechargeable batteries. So it generates its own power. The mooring riser then consists below the buoy, regardless of the type of buoy. There's a 5-meter EM chain and then a near-surface instrument frame, which holds a variety of instruments down at about 7 meters water depth. There's then, depending on the depth of the mooring, a variety of either EM cable and or EM stretch hose to make up the water depth. And then at the bottom is this, what we call multifunction node. It consists of a benthic anchor recovery frame. In the case of the Oregon shelf and offshore sites, all that frame is an anchor recovery system because we don't send power to the seafloor. On the inshore sites and the high power surface moorings, we actually do send power to the seafloor, and so there are power, platform control components, and instruments down on the seafloor on the multifunction node. And you can see in our cryptic coding what the different instruments are in these different locations. This shows what some of the infrastructure looks like. On the left, you've got the coastal surface mooring. You can see the tower with a variety of meteorological instruments and telemetry components up on the top. You can see the solar panels both on the wind vane and on the deck of the buoy. And it may be a little hard to see, but these are wind turbines on the side of the tower here. The central picture is the submersible buoy used by the Endurance inshore moorings. You can see some instrumentation that is mounted to the base of that buoy. The upper right is the near surface instrument frame, where a variety of instruments can be mounted at about 7 meters water depth, and then the bottom is the multifunction node. And as I mentioned, this consists of a buoyant frame, which enables us to retrieve the mooring, and then beneath that is the anchor, which has its own recovery system, because we do have to recover all of the anchors. So the anchor and the recovery module fit in the center of this structure, and around the outside we have instrumentation. This is a diagram that shows what the coastal surface mooring looks like. I'm going to show you a similar diagram on the next slide of the inshore mooring, and you'll see that there are just a couple of differences. This mooring has power generation, so we have rechargeable batteries, the turbines, and the PV arrays. There's all the telemetry. There's redundant telemetry in the case of these moorings, platform control components in the buoy, in the near surface instrument frame, and on the seafloor, which enables instruments to be collected at those, instruments to be plugged in at those locations. And once again, that's the 12 or 24-volt power and serial Ethernet communications. The inshore mooring is almost exactly like this, except that it has the smaller buoy up here, which means there's no power generation. So power is provided by lithium batteries, both in the buoy and on the seafloor on the MFN. And we only have single telemetry in this case. When we have no fleet broadband telemetry, so the surface moorings actually have a Inmarsat fleet broadband system, which gives us high power telemetry. This shows where surface moorings can have instrumentation added if needed. The buoys on both flavors can have instruments connected to them. The near surface instrument frame. On deeper moorings that have EM cable sections, it may be possible to clamp instrumentation to the wire, but no power communications are available for instrumentation that are clamped onto the wire there. And then the multifunction node at the bottom. Once again, as I said before, the addition of any instruments requires this kind of reanalysis process to make sure that the mooring is still structurally stable. So now we move on to the global surface mooring. This is very much like the what we call the standard power coastal surface mooring. So it has a surface buoy, which is similar to but slightly larger than the coastal surface buoy. It has the same type of platform control components, the same types of dual telemetry, including the fleet broadband, high bandwidth telemetry, the wind turbines, solar panels, and rechargeable batteries, and similar mooring riser components down to the near surface instrument frame. In this case, there's a longer EM chain that has the near surface instrument frame hanging at a depth of about 12 meters. And then below the near surface instrument frame is a section of inductive wire, and then acoustic releases below that. So instruments that are located on the buoy and on the near surface instrument frame are powered by the mooring system. Anything mounted on the inductive wire is self-powered and communicates only inductively. This shows what the buoy looks like. So this buoy is exactly the same as the coastal surface buoy, except that it's got an extra foam section added here, and the tower is 3 feet taller due to the higher wave conditions at the global sites. You can see here the picture of the halo. There's also a photo here and a diagram here where we've got the telemetry components scattered as well as the meteorological sensors. And then this is the diagram of the near surface instrument frame. So as I said, this is like a standard power surface mooring. Power and communications only go down to the NSIF, and there's only inductive communications below that. Inductive instruments can be mounted all the way down to 1,500 meters water depth. So in terms of adding instrumentation, once again, they could be added to the buoy, to the near surface instrument frame, or clamped onto the inductive line. There's also a frame that contains the ADCP at 500 meters. Anything mounted below 1,500 meters, we cannot communicate with inductively, so it would have to be self-powered, self-logging, and we wouldn't get that data back until recovery. This is the case for the OSNAP instruments that are at the bottom of the Erminger flanking moorings, same type of thing. The flanking moorings, as I mentioned, the global flanking moorings and the global profile moorings are both subsurface moorings, so these are a little bit different than the other moorings we've been talking about. They have a low power controller, which there's a controller up here in this upper sphere where most of the a number of instruments are located. There's then another controller down in this load cage accompanied by an acoustic modem. And then there is instrumentation mounted on the inductive wire between them. So all data is communicated inductively down to the main controller here. The data can then be transmitted acoustically to a glider in the vicinity that can then send that data home by satellite when it surfaces. Likewise, commands can be sent back through that same path if needed. And I will note the instrumentation that's located on the inductive line here below the mooring, below the upper sphere, is similar and at the same depth to the instrumentation that's on the global surface mooring. So the two flanking moorings and the global surface mooring, which make the three corners of the triangle, are all making the same measurements at depth. These show some of the components of the flanking moorings. These are the top spheres, which contain some instrumentation at a depth of 30 meters. This sphere contains the ADCP. It's at a depth of 500 meters. And then this is the controller cage, also seen in the top right being deployed. And then we have, because we have multiple flotation elements in this mooring, we actually have a release in the middle of the mooring to separate the mooring into two halves. This makes it easier and safer to recover. So this gives you kind of a block diagram look of what happens. Like I said, there's some instrumentation up in the sphere, which is connected to the secondary controller, the acoustic release to separate the mooring in two halves, ADCP in a sphere. All the data comes down to the main controller where it's then sent out acoustically. So in terms of adding instrumentation to this mooring, there is some space in the 64-inch sphere at 30 meters where instrumentation can be added, once again clamped on the inductive line, anywhere down to 1,500 meters depth, in the ADCP sphere at 500 meters, and also in the load cage. And the profiler mooring, so this is very much like the flanking mooring, except instead of fixed instrumentation, it has profilers that go up and down. So there is only a main controller. It's located in a load cage at the bottom, same as the flanking moorings. Once again, telemetry along the mooring is all inductive, and telemetry off the mooring is acoustic. It's powered by primary batteries. The upper sphere is at 150 meters, and it has bioacoustic sonars that look both up and down. And then in most cases, there are two profilers with a midwater sphere in between. At the Erminger site, which as you'll recall is our shallowest site at around 2,800 meters, there's only one profiler, so there's no midwater sphere. This is what some of the components look like. On the left, you see the profilers there, one being deployed, and then on the right is the upper 64-inch sphere. As it's being deployed, this is deployed at 150 meters, and you can see here the transducers on the top and the bottom here for the bioacoustic sonar. And so, once again, this is the diagram that just shows what that looks like. So, as with the other moorings, if instrumentation were to be added, it could be added to either of the spheres, clamped onto the inductive wire outside of the range of the profilers, or mounted in the load cage. All right, so now we're going to talk a little bit about the vehicles. The first one is the Coastal Surface Piercing Profiler. We're referring to this as a vehicle because it's kind of an independent vendor-provided instrument package. This is another way to refer to it. This is a Wet Labs AMP, and you can see the list of instrumentation that it contains. This is being deployed on the endurance array at the inshore and shelf sites. You can see there's a anchor system to the side with a section of chain, and then this profiler operates completely on its own, so it has buoyancy and it has its own winch. So it winches itself to the surface, making measurements along the way. At the surface, it can communicate inductively, it can communicate through iridium, and then it can go back down and stay on the bottom out of the way where it's safe. Coastal gliders, we have the coastal gliders at the same coastal gliders at both the Pioneer array and the Endurance array. These are Teledyne Web G2 slocum gliders. And we have two types of buoyancy engines that are used, the 200-meter and the 1,000-meter engines, and these are just depending on the depths that these units are being deployed at. The instrumentation package is the same for these moorings, as you can, or for these gliders, as you can see listed there. At the Pioneer site, this is what the primary glider track lines look like. So these small circles here are the moorings that you saw previously in the mooring array diagram. And then the solid lines are the areas where the gliders are transiting. So there's the eastern boundary line here, and you can see that line uses a 200-meter engine. There's a frontal zone track line here, which is traveled by two gliders. You can see here FC1, FC2. This Argyle pattern is the Slope C track line, and then the Gulfstream one shown here in gray. In addition to that, I mentioned that the inshore site and the central site where we have wireframe profiles in the winter, we'll actually be using profiler gliders in the summer. So they will operate in the vicinity of those sites, doing a number of profiles a day. They have a slightly different suite of instrumentation. This is actually the same as the global profiling gliders, which I will show you in just a minute. The Endurance coastal gliders have a number of lines that you can see here. They're all numbered along here, so you can see the lines that run along the coast and out from the coast. And once again, different buoyancy engines are used depending on which portion of the line is being traversed. At the global sites, we have what we call open ocean gliders. These are the gliders that transit around the outside of the array. They collect data in between, as I said, and serve as data mules, transferring data to and from shore. They have only a couple instruments, and of course they have the acoustic modem for communicating with the moorings. The global profiling gliders are the gliders that operate in the vicinity of the profile and mooring to make sure we get profiling measurements in that upper 200 meters. So they can hold position down at 1,000 meters to stay kind of safe and out of the weather. They profile the upper 200 meters a couple times a day, and once again you see the larger suite of instruments, just like the coastal profiling gliders. And then we have the Autonomous Underwater Vehicle, or AUV. This is a REMUS 600 from Kongsberg Hydroid. It has an instrument package very similar to the gliders. There'll be two AUVs operating in the Pioneer array. They'll basically be doing 2-day deployments from a ship once a month. They operate from the surface down to 600 meters. So you can see here these little dots, or perhaps they're squares or diamonds, I'm not sure from here. Those are the actual moorings, and then the lines are the transects, horizontal and vertical transects. All right, so in terms of opportunities for interacting with either the Pioneer, Endurance, or Global arrays, there is obviously a website, which most of you probably know about, which is probably why you're on this WebEx. So there's a couple different things you can do. One is connect new instruments to the observatory network. There's two ways to do that. Obviously the easiest is to simply have self-powered, self-logging instruments mounted onto the infrastructure to collect data that can then be retrieved on recovery. The other way is to have instruments that actually connect to our CGSN infrastructure, that is, connect to the DCLs that I mentioned earlier, get power from our infrastructure, and send the data back through our telemetry system. Another thing that can be done is the sample rate of the existing instruments and platforms can actually be modified. So you could have a proposal to, say, increase the sampling rate if a hurricane of a certain strength is, say, coming up the East Coast through the Pioneer Array. We would have to vet that change to make sure that the infrastructure could do it, the instruments could sample at that rate, and that the power wouldn't cause problems for the duration of all the infrastructure. But once that was vetted and approved, then that's something else that could be done. And then there's also the opportunity for doing ancillary work during our normally scheduled OOI cruises. We've done some stuff like this in the past, such as deploying gliders or floats for some people at some of the global sites. And then kind of, even thinking down the line, longer term opportunities, deploying another type of platform in an array to make complementary measurements, helping to improve some of the engineering capabilities of our infrastructure, and adding techniques for calibration for deployed instruments. So the process for actually connecting new instrumentation would be, identifying some candidate instruments, then consulting with us here at OOI or at Oregon State on our engineers to determine the viability. So we will check out if the instrument will fit, if we can power it, how the communications would be, and provide a letter confirming the technical feasibility and the schedule and cost. There may be ship time may need to be requested depending on the extent of the ask. Obviously, the proposal needs to get funded, and then once the instrumentation is developed, it can be integrated and tested and deployed on the infrastructure. We do have extremely rigorous testing, so I guess one thing to keep in mind is, once something is funded, it will be a fair amount of time that it needs to come and be ready and tested with our infrastructure before it's deployed. It's not a send it and it, as long as it gets on the boat, it gets deployed. It has to go through rigorous testing before we can put it out there. So once again, I want to remind you of the points of contact. There are some general contact points, such as the OOI Help Desk, which can be reached through website or by email, help@oceanobservatories.org. There's obviously the leads here at OOI and at Oregon State who you can get in touch with, and the project scientists responsible for the various coastal and global arrays. And that is the overview. So at this point, if there's any questions, we can try to address them more specifically.
And you all should feel free to answer questions either through the typed-in Q&A interface, or you can raise your hand. There's some little action icons where you can raise your hand and we can unmute you if you would like to ask a question. Here we go. It looks like we have a question coming in from Fritz Starr, and he says, will this presentation be available somewhere online for future reference? And yes, it will be. We're going to be posting a recording of the video to YouTube, and then it'll be on our website. And then we will also be posting a PDF of the presentation. All right, we have a question in from Kate Tremblay. Will there be opportunities for grad students to go on cruises to learn and assist for the Pioneer Array?
Yes, certainly. We would welcome that, and probably the best bet would be for an interested student to email me, Paul Mathias, with a little background information and a little more specifics about their interests. But I think we would welcome that, and we would mutually benefit from that experience.
And by the same token, there's certainly bunk space available on the OOI endurance cruises. As folks are probably aware, that the cruises occur for both Endurance and Pioneer twice a year, a spring and a fall turn cruise. On the Endurance cruises with global class ships, we generally have bunk space available. What we tend to have a little bit less of is wire time or the ability to do adaptive sampling. You know, we're kind of locked into our mooring turn cruise. But having said that, there's certainly opportunities for graduate students, I think, in general, to do to assist with CTD sampling and to assist at least in some small way with the mooring operations.
And one thing that we should note, too, in terms of thinking about the opportunities to use OOI data and be a part of the OOI, is that anyone can use the data. You don't need to have an accepted NSF proposal. You can just go online, download the data, use it in an analysis, publish it. There's no restrictions on the use of OOI data. The only thing we ask is that if you do use our data in a publication, that the OOI is in the acknowledgement section and you acknowledge the source of the data. But so anyone and everyone can use the OOI data, but you're also welcome to, as I discussed in these presentations, to write proposals to either add infrastructure to the OOI or to answer a specific science question using the data. So there's lots of different ways to get involved.
Leslie, there was one question, I saw the attendee list. There was one question from Thomas Norris, who I think is not attending online, but he submitted a question about hydrophone and bandwidth specifications, and that was one of the questions I was thinking about in terms of passing things on to the University of Washington. The hydrophone is part of the cabled part of the endurance array, so the best place to direct those kind of questions to is to University of Washington. Having said that, I can get back to Mr. Norris with the make and model. As a general note, on the oceanobservatories.org webpage maintained by CI, all of the instruments that have those those 5-letter acronyms that Sherry referred to are called out on the oceanobservatories.org website by their make and model number, so that you can find out general information there and get more specific information from engineers at the OOI organizations.
All right, well, that looks like that's all the questions we have. Yeah, thanks everyone for coming out, and I'll turn it back over to Paul Mathias.
All right, Leslie, thanks very much. Again, the materials will be posted to YouTube. There are contact details for folks at WHOI and OSU that can be reached offline through email or telephone, and we'd welcome the opportunity to field any questions or opportunities to collaborate. So with that, I think we'll sign off here from OOI, and thanks again for dialing in.